Remain, Evelyn, if you're there, can we get videos on? And Happy also. And can we all look smart and presentable because we're going to be live? This is your TV debut, unless you've been on TV before, that is. Sometimes on the Habitable Planet channel, we have almost 100 viewers. You know, that's quite a big TV show. Okay, we're up and going. Let me get the link, copy. Someone needs to say something. Patuma, are you there? Patuma is the chair. Maybe you can just tell people we'll be broadcasting shortly. The talk will start shortly.
Okay. Huh?
One minute.
Wait.
Okay. I'm aware that it's time. I'm still just doing this. I will be with you in a minute.
Should I start now, Doctor?
Just give me a minute. Just give me a minute. I'm aware that it is time, but I've just got to send the link around. Nearly there, I promise. One more place to send the link and we're good. And my computer is obviously being slow because it knows that there's time pressure. All right, Patuma, I've advertised it everywhere. You may go ahead and share.
Oh, okay. Something is moving awkwardly. Good afternoon, everyone. Welcome to our afternoon session. And today we have Professor Willem Landman, all the way from the University of Pretoria. He's one of the most smart, intelligent professors of the Axis. He's one of our scientists. So this evening, or rather this afternoon, he's going to be giving us a talk. Please listen attentively, comment, ask questions, and participate. We will now hand over to Professor Landman. Professor Landman, welcome, and please do give us your talk.
Yeah, good afternoon, everybody, and thank you for listening in. I hope I come across quite clearly, and so I'll try to speak a bit slowly so that the internet can handle my voice better, I suppose. Today we will be talking about making forecasts or predictions, and the talk will focus almost entirely on the seasonal timescale. Now, what do I mean by that? By seasonal timescale, I mean that we are making forecasts, for example, will this summer that's coming going to be wet or dry? Or will this summer that's coming going to be hot or cold? So it's not like the weather forecast where we will be predicting, for example, what is the chance of getting rainfall tomorrow at 3 p.m. over Table Mountain? It's quite different to weather forecasts, but we kind of use the same models to make seasonal forecasts than the models that we are using to make weather forecasts. So what I will try to show in this talk is that there are major advantages in making forecasts as opposed to just guessing what the season might be like. So if you go to the first slide, on this slide, this is actually a very well-known graph that shows forecast performance over both the northern hemisphere and the southern hemisphere for an atmospheric variable, in this particular case, how good these models are in predicting the mid-tropospheric weather condition. So we have forecasts for days 3, 5, 7, and 10. That means forecasts 3 days ahead, 5 days ahead, 7 days, and 10 days ahead, with a thick line representing forecast skill over the northern hemisphere and the thin lines with the southern hemisphere. There are a few things that we can immediately recognize from this graph. Number one, the forecasts are improving over time, because on the x-axis you can see the years from 1981 to 2007. That shows that forecasts are improving. Now that's actually quite a relief, because we spend a lot of time and effort, and obviously also money, in improving weather forecasts. So it's good to know that our efforts are actually paying off. We also see that the southern hemisphere has caught up with the northern hemisphere. And the reason for that is mostly because our observations, our systems in making observations of the Earth system have improved considerably. But what we also see is that once we get to about 10 days ahead, we have reached some predictability limit. So if you look at some of these weather apps that you find on your phone, you can see they're making forecasts up to about 2 weeks ahead. Well, actually, I wouldn't really trust any forecasts that go beyond maybe 7 days for South Africa. But the point is that we get to a time where we predict days ahead when weather forecasts fail. It actually means that guessing in that case will be better than the forecast. But anything up to about 7 days, the forecasts are doing really well. So my grandmother, who has passed away a couple of years ago at the age of 102, she asked me this question: you can't even get the weather forecasts right. Obviously, she was wrong to say that. But she asked a very important question. If you are struggling to make weather forecasts, how on earth are you going to have any success in predicting what the season might be like months ahead of time? Now, that's a very legitimate question. So that's the question that we need to answer, because if we want to make forecasts, there's got to be a scientific basis for making such forecasts. And the next slide gives us some indication of what that scientific basis might be. When you're looking at seasonal timescales, that's the average conditions, for example, over a couple of months from now over the summer season, we cannot expect to find any ability to predict, for example, there's going to be a thunderstorm over Pretoria 3 months and 7 days from now. That thing that I've just given as an example is not predictable. But we can say something about seasonal averages. For example, will this coming season, on average, be a bit wetter than usual? That's a legitimate question, and that's something that we have tried to predict. And as you will see in this talk, we have been able to do this quite successfully in some cases. But what is the reason behind this predictability? And on the right of this slide, you'll see 2 maps. The top map shows sea surface temperature anomalies. Now, an anomaly is just a departure from an average. And when you see red anomalies, it shows where the sea surface temperatures are anomalously warm. And if you know your geography, you can see that in the center of that figure, you'll see we are looking at the Pacific Ocean. And the biggest warming there is over the central equatorial basin. And it's interesting to note that when there's a very strong warming, the temperatures, the real temperatures, not the anomalies, the real temperatures over that Central Pacific Ocean basin can be in excess of 32 degrees Celsius. It's amazing to think that seawater gets as warm as that. Now that top figure shows what the sea surface temperature anomalies looked like during the 97-98 season. Very strong El Nino event. The bottom figure shows sea surface temperature anomalies during the 1988-89 La Nina. Now, El Nino is a term that we normally use for the time when sea surface temperatures over the Central Pacific Ocean is really warm. And a La Nina is the term we use when sea surface temperatures over the Central Pacific Ocean are really cool. El Nino is Spanish for boy child, and La Nina obviously for little girl. And so El Nino and La Nina events are the most important driving force behind seasonal predictions, especially over areas such as Southern Africa. So we can make forecasts. They are slightly different to weather forecasts, not as detailed. And the reason why we can is because these El Nino and La Nina events are present and they evolve really slowly over months of time that they take for developing into a mature event. And when these events become mature, they influence global circulation patterns. So the influence from El Nino and La Nina is felt all over the planet, and it's really strong over some areas, less strong over other areas, and intermediately strong over other areas such as Southern Africa. The next slide shows the intensity of El Nino events. Now, this is from the so-called Oceanic Nino Index. There's the website address at the bottom. And what we immediately see from this time series that shows the strength of El Nino and La Nina events, all the values above the 0 line are warm sea surface temperature anomalies, and all the values below the 0 line are cold sea surface temperature anomalies over that important Central Pacific Ocean basin. And what you can see is not a single El Nino or a single La Nina event is similar to each other. They are all different in terms of intensity. So these events are so different in intensity, you can imagine, knowing that they have an impact globally, that their footprint will be different from one season to the next. If we look at the next graph, next slide, we'll see where El Nino and La Nina events have their biggest impacts. On the left, you'll see some of the earlier work, results from some of the earlier work done in the 1980s. And it shows areas where we have warm or cool or dry or wet outcomes as a result of El Nino events. On the right, you see a more modern representation. It's not a lot different to what we see on the left, but the latest data that were used to see the impacts of El Nino and La Nina event are reflected on the two panels on the right. And what we see for Southern Africa, when we have an El Nino event, it's mostly dry. And when we have a La Nina event, it is mostly wet over Southern Africa. So it would be great if we can know ahead of time whether or not there's an El Nino or La Nina coming, because they have such strong impacts globally. By just having some indication of whether or not there's an El Nino or La Nina, or what we call a neutral condition when there's neither an El Nino nor a La Nina, we can actually say something about what the season might be like. So can we predict these El Nino and La Nina events? And the next slide shows an example of a very complicated, fully coupled ocean atmosphere model. Now, this is state-of-the-art models developed by the European Center for Medium-Range Weather Forecasting, predicting the El Nino event of 97-98. The black line represents the actual observations, how the sea surface temperatures varied over that period. And you can see the sea surface temperature anomalies reached about 4 degrees Celsius. And this is an example that I've used before, where the real value, the actual values of the sea temperatures over that Pacific Ocean area was about 32 degrees Celsius. Now you can imagine how warm the sea surface temperatures must be. This results in a lot of evaporation, and as a result of that, deep convection. And these very strong convective patterns, and like I've said before, influence global circulation patterns. But what I'd like to also point out in this graph is forecasts produced at different times on that black line, which is that shows the evolution. We have different forecasts making different plumes of forecasts. It looks like a broom, end of a broom, you know. And what we see there is that even on this time scale where we know El Nino and La Nina events are highly predictable, that there's some uncertainty in the forecasts. Look, for example, that third initialization, the blue one. It shows that the plume, if you look at the more or less an average of the plume, it's below what is actually observed. But if you look at the full extent of the plume, it does capture the observation. Then as we go to the next initialization, the orange one, it overestimates the anomaly. So that time the model says it's going to be getting a lot warmer, and actually it didn't turn out to be as warm. And so you see, even on this time scale where El Nino and La Nina events are highly predictable compared to other things, there's some uncertainty still associated with it. Okay, so now we've just talked briefly about our ability to predict El Nino and La Nina events. But we want to know something about the predictability over us, because this is where the decisions need to be made. Decisions are not made in the Central Pacific Ocean in terms of our economy, for example. The decisions are made on what we are experiencing here. So the next slide shows us some indication of how good we are in making forecasts. So let's first start off by looking at that graph on the left that show the 3 yellow bars. Now we have those bars representing different forecast models. And I'm not going to go into much detail other than saying that these models are varying in complexity. The model on the left is the simplest of the 3, and the model on the right is the most complex of the 3. Those values on top of the graphs, they tell us how many rainfall districts in South Africa out of 92 districts have actually been found to be predictable on during the midsummer period of December, January, and February. And what we see is as models are becoming more and more complex, forecasts tend to improve. Now that's also quite a relief, because like with weather forecast models, we spend a lot of time and energy in making forecasts and better models. So if all our efforts have produced worse forecasts, we would be in trouble. This is quite a relief. Forecasts are improving. Now on the right, top right, you see something that's got nothing to do with seasonal forecasts. But what it represents is cell phone sales, in particular the iPhones. And you see iPhone sales have been increasing. So why is that? I think it's because the model, the phones are becoming smarter. It's a smartphone that's becoming smarter and smarter. People want that. So you see higher sales because the phones are fancier, can do more things. And this is not too different to what we have found with the seasonal forecast performance on the left, that shows improvement in skill as models improve. However, now this is a big problem. We think that people are not using forecasts as much as they should, because the skill is improving, but the use is not. Now, how is that possible? And I'll try to highlight some of the challenges that we face, especially over regions such as Southern Africa, where predictability is limited to some extent on this particular timescale. One of the limitations is shown in the next graph. This shows our ability to predict rainfall over Southern Africa during El Nino events, during La Nina events, and during times when there's neither an El Nino nor a La Nina. And so the black bars show our ability to predict wet seasons. This is during the midsummer season. And the white bars show our ability to predict dry seasons during the midsummer. So during El Nino, we are better able to predict dry conditions. We also get occasionally a wet El Nino that we also seem to be capturing. We see that we can predict very well wet conditions during La Nina, and occasionally when we do get dry conditions during La Nina, the models also seem to capture that. So that's fantastic that we can do this. But what is really disappointing is that when there's neither an El Nino nor a La Nina, it really doesn't work. Now, this is using state-of-the-art models. And even the recent models, the most recent models that I've looked at, continue to have this problem. We know that there are other factors also influencing Southern African rainfall, like, for example, the Indian Ocean dipole. But the models don't really seem to know how to handle that in predicting Southern African rainfall. So to summarize this slide, it says no ENSO, El Nino Southern Oscillation, no ENSO, no skill. So what do we say to a farmer that's desperate for rain when there's neither an El Nino nor a La Nina? We have to tell him, sorry, my friend, it's best not to use a forecast. Does that instill a lot of confidence? Maybe not. Maybe not. This is one of the challenges that we face. And on the next slide, which shows a map of areas influenced by El Nino and La Nina events and how their skill scores, how good they are at how good the models are at predicting rainfall, compare with what we have over Southern Africa. So when you see green areas, it shows areas where their forecast skill is comparable to our forecast skill. When you see yellow, there are only two examples of those. Very importantly, the example of the Southeast South America. They have a 95% confidence level that shows their forecasts are quite a bit better than ours. And the red one shows at 99%. Their forecasts are way superior to our forecasts. So we can see that we actually don't rank very highly. In fact, if you look at all those figures in those boxes, we rank about 14th or 15th out of 20. So there are 13 or 14 areas that do better than us. So we have this challenge that the seasonal forecast skill is not so fantastic over us compared to other areas. And the next graph shows you some idea of when we have been able to make fantastic forecasts and when we have failed miserably. Now, if you look at the time series there are three. The thick black line shows the actual observations in millimeters. This is from a paper we wrote in 2012, and there's actually a mistake that neither us nor the reviewers picked up on, and that is that the rainfall values that I have on the y-axis is too low. You should actually multiply those values by 3. There's an example of something that slips through in a publication, which is a bit of an embarrassment. But nevertheless, it shows important things here. It shows the observed, the black, and forecasts from two coupled systems that have been combined in through different statistical processes. I'm not going to go into much detail. But if you look at some of the years, the thin lines and the thick black line actually correspond quite nicely. But when you look at that 97 case, that's the big anomaly predicted by the models, it is nowhere near the observation. Look at that. That is a huge problem, because the example that I showed earlier on the sea surface temperature anomaly maps, that 97, 98 El Nino was enormous. It was really strong. We've had a recent strong one in 2015-16 that was as strong as 97, 98. So we see that in that particular case, when models predicted dry conditions mostly as a consequence of that strong El Nino event, it really didn't turn out to be that dry. It wasn't wet. Thank goodness for that. It wasn't a wet season, but it was nowhere nearly as dry as what we anticipated. And that really damaged our reputation as the scientific community trying to predict what the season might be like. When we were predicting months ahead of time that we might face droughts during that season, we had farmers groups visiting us. We were on television. We had panel discussions. It was a big thing. We made it clear that our expectation is drought. And it didn't turn out to be that dry. And that really damaged our reputation as a science effort to make forecasts that are skillful. The next slide gives us some indication of when and where, actually more when, forecasts over South Africa actually do work. I'm not going to go into much detail again, but I'm going to point out some features that I think are important. If you look at the top panel, you can see seasons on the x-axis, September, October, November through February, March, April. And then you have numbers on the y-axis, 1, 2, 3, 4. Now those numbers represent forecast lead times. So this is a forecast made for the, for example, if it was for DJF, December, January, February, that number 1 means that we have made a forecast in November for December, January, February. And number 2 means that we have made a forecast in October for December, January, February. What we see as white areas and blue and green and some red areas. Where we have white, it means forecasts simply have no chance of working. Forget it, they don't work. And this is mostly associated with springtime. When we move into midsummer, we find that forecast skill improves significantly, and I have to add that the skill analysis here was done for wet seasons. And I'll explain to you a little bit later on why I'm focusing on wet here, as you'll see in the next examples. So we have the ability to predict skillfully during midsummer with lead times up to 3, maybe 4 months ahead of time, whether or not we will get wet conditions. The graph on the bottom, that's really complicated. But what you want to see is the thin lines representing a weighted average of the curvy lines that shows the association between forecast probability and observed frequency, which translates into the reliability of a forecast. You want to see those thin lines fall right on top of the diagonal black line. The blue line is representing wet seasons, and the thin red line represents dry seasons. And you can see that the blue line is much closer to the diagonal line, which tells us something about how reliable are the forecasts in terms of a probabilistic forecast for making wet season predictions. And you can see it's actually not too bad. When we come to drought forecasts, we are not very good at making that, unfortunately. And I'll demonstrate this example in the next slide, what consequence that might have. Here we have a forecast on the right, issued by the International Research Institute for Climate and Society. Now, that's a very good institution in terms of making seasonal predictions. And you see over Southern Africa and includes parts of northern Namibia, where you see the color of the area to be dark orange and brownish, which represents the high probabilities of dry conditions. This was during the 2015-16 very strong El Nino event. So the models like they normally do when there's such a strong event, make Southern Africa dry. And they were quite confident that it will be dry over northern Namibia. Now, on the left, you'll see a bunch of time series. It's a bit of a dog's breakfast. It's difficult to distinguish all the different lines. But the blue line represents the rainfall time series over a long period of time over that part of Namibia that I just referred to, that northern part of Namibia that includes towns like Grootfontein, for example. And you see that outcome is different to the outcomes of the other areas that include the northeastern parts of South Africa and central South Africa. So that northern parts of Namibia actually was not dry, although there was high confidence that it might be dry. But we have seen in the previous slide, when we talk about Southern Africa, we are sometimes overestimating our ability to predict drought. And that's a big challenge. And to fix that, we are much better able to predict wet seasons, especially when the prediction is for wet during a La Nina season. I don't have any slides to prove that point, but here's an example of where a forecast verification could have given us some insight in the forecast use, because we could have warned the user. The forecast is for dry, but we've seen through our verification work that drought forecasts are more risky to use than wet season forecasts. Now, the next slide will answer the question. Although I've presented now 2 examples where forecasts may have failed miserably, is it making any sense to use models? Because I've just pointed out 2 examples where it was quite embarrassing that forecasts for really dry conditions didn't turn out to be this way. So we tried to do this analysis for a farm over in the northern parts of Namibia, and we did a verification. And again, without going into too much detail, we did a verification work over that red part of the time series on the left-hand side. And the verification parameter that we used is the so-called ranked probability skill score. And how to calculate that skill score is shown on the top. And what I would like to draw your attention to is that bar chart on the bottom right, the one that has only the blue bar charts. And to summarize that bar chart, it tells us one thing, and it's a very important thing, that making use of physical models is better than guessing. It's better also than using our earlier on when we talked about El Nino means drought and La Nina means wet. When you make that kind of a kind of what I call a homemade model, our physical models that we use, even though they have their problems, that's still the way to go. We are still doing a better job than guessing. Now that's great. So that means that we can take the next step. And what is that next step? This is what the next graph, the next slide I think is trying to show, is trying to use all the things that we've developed, all the knowledge that we've gained, and we've been doing seasonal forecasting more or less from the early 1990s. So we've been doing this now for quite a long time. And we've learned a lot of lessons in the process. And we've been embarrassed in the process as well with our forecasts that have turned out to be not useful. But we've also had fantastic successes. One of the great successes that we've had was during 2009-10 when we had a La Nina event. And we predicted that really skillfully. And we also predicted that really skillfully for large parts of SADC, not only South Africa. So what we have done now is, in addition to the regular forecast, which is shown on the right, on the left. On the bottom left, you see a typical forecast map of the likelihood of it being dry and the likelihood of it being wet. In this particular case, it was for September, October, November 2019. This is the kind of forecast that we issue frequently at the University of Pretoria, and most notably, of course, the Weather Service, because they are the custodian of making forecasts. And what I see just on top of that map is the actual outcome. And you see large areas of brown, which is showing areas where it didn't rain a lot. It was quite dry, which is a good agreement with the actual observations. And in the middle panel, you see forecasts that we've developed for the inflows into Lake Kariba and forecasts in predicting malaria outcomes. And on the right, you see making forecasts for crop yields at the end of the season. And you can see that we've demonstrated here, I have limited time left, demonstrated here that we can actually say something about rain, the derivatives of rainfall. Not rainfall itself, but flows in a river. Epidemics that have a strong climate signal like malaria. And dryland crop yield that is also obviously strongly linked to rainfall outcomes. The next slide is showing an outcome that that shows that we have to be really careful when we make forecasts. Without going again into much detail, you can see in the middle of that graph on the left, you see there's big discrepancies between the forecasts, the red time series, and the observation, the blue time series. And that's reflected in how much money the farmer would be making or losing as a consequence of poor forecasts. And what this graph on the right actually shows you in terms of cumulative profits, that if we have a situation where we have failed in 3 consecutive seasons, in summary, it can take as much as 8-9 years for the farmer to recover from forecasts that have been really poorly made. The next slide shows where we have tried to focus on particular farmers. Those farmers have given us their rainfall data at their farms. We've developed models for them, and we have also done some financial analysis on how well they would have been performing money-wise if they used the forecasts. The top one shows an area for a farm over northern Namibia, which is a farm different to the one I showed before. And the one on the bottom shows a farm in the Southwestern Cape. Nobody thought that we would be able to make forecasts for the Southwestern Cape in the seasonal timescale, but we've recently shown that we can. But this case shows that the recent years, the forecasts have not been successful, and that is reflected in the cumulative profits, because if you look at the cumulative profit graphs, it goes beyond the red line towards the end, which means that in that particular case, the farmer may have maybe made a bit of a loss. And in conclusion, I hope I'm still within my time limit, Carl. The conclusions to be made here are ENSO, El Nino Southern Oscillation, for the most part, determines our predictability. I'm not claiming here that nothing else matters. It just seems that ENSO seems to be the biggest contributor to our predictability. We have seen that forecast models have improved because of the more complexities involved. The more complex the models are, the better the forecasts are. We have seen also quite strong evidence that forecasts are better than just guessing, which is quite a relief. We have to, nonetheless, when we issue forecasts, give the user some indication of how good these forecasts are. And if we are irresponsible, we can find that our poor forecasts can have serious financial implications to the user. But one of the ways to cater for this is to what I tried to present in the previous slide, is to start to collaborate with farmers and to co-develop models with them by using their data and co-learn from the process. And hopefully that will improve our understanding of forecasts, what the different needs are for the users, and how we can ultimately improve on forecast update. Thank you, Carl. Thank you, everybody, for listening.
Thank you so much, Professor Landman, for such an informative talk. It was really nice having to understand how our focused and predicted or guessed, or which one is the. I have a sound.
Sorry,
the recording playing. Yeah, your sound is a bit funny. Try again.
How is it now?
Oh, yeah, much better.
I was thinking, are you still doing the same thing, Dr. Carl? Oh,
Try now, Patuma.
I was basically thanking Dr. Landman for such an informative talk. It gave us an understanding of how the predicting of our focused goals and how it affects local farmers. So what we're going to do now is to go for a round of questions from Planeteers. So guys, Dr. Carl, can you please help me in noting hands of questions or comments or something you'd like to add or say in what Professor Landman has said. So the floor now is open for questions.
Okay, there is me and Lucinda.
Okay, let's start with Lucinda.
Thank you so much, Professor Landman, for the key lecture. I have a question in terms of the poor weather forecasting. Sorry about the noise. Does how evolved a country is in terms of technology have an effect on how poor or how rich the weather forecasting is?
Yes, if you have resources to help with model improvement, of course, you will see that your forecast also improve as a result. On the seasonal timescale that I presented now, we see that the more complex models are making more forecasts, a better forecast. And I know the Weather Service of South Africa has a big program where they do model development. And the reason why they can do it, because they have the money to pay the scientists to do the work. And they have money to collaborate with large institutions like the UK Met Office. And because they have money, they can actually use that money to help those people interested in making models perform better to work for the Weather Service. And so if you don't have the resources, obviously you will not be able to invest that kind of money into model development. But that's not the end of the story. The seasonal forecasts that the University of Pretoria produces uses some of the forecast models that are run in the United States of America. So poorer countries will be able to get forecasts from big centers through the World Meteorological Organization and make forecasts for their region based on other people's models. But I think you have a good question. I think the answer is, if there's money that can be spent on improving models, that country will definitely benefit.
Thank you so much, Prof. Thank you.
Thank you for that, Dr. Carl.
Nice one. Thank you, Madam Chair. Thank you once again, Professor, for a really interesting talk. And I was very happy that this time a lot of the graphs were a lot more simple. There was some towards the end that each time I really have to concentrate to try and interpret. The one of them I wanted to ask about, on slide 8, I can quickly show it for everyone, I guess. It's just use my privilege of being able to share my screen. This graph on slide 8, showing the predictions for Southern Africa for El Nino and La Nina events and neutral. And I wanted to start, my first question is, neutral being less than 0.5, does that mean it is less good than guessing? Are you with us, Willem? I think we've lost him. See if we can get him back. Did everybody see that slide? We just don't have Professor Willem. That is definitely a problem. Is he coming back? No, he's just gone completely. Well, we might have to conclude, I guess. Let me just give me a second to see if I can get him back whilst you all think about questions for when he does come back. Bear with us a few minutes. Tomelo, not Willem. Messages to his WhatsApp are one tick, they're not going through. So I'm guessing we're going to have to call it there, as I can't get in touch with the professor. I will hopefully be able to put any questions that you may have to him at some other points, or maybe try and get him back at some point. So for everyone watching on YouTube, you're very welcome to send us questions on our social media, and I'm sure the professor will answer them there. For everyone here in the studio, you're off the hook for asking questions today. Hopefully we'll get a chance to talk to the professor again later. All right, guys, I'm going to end it there. Thank you very much.